All right. Welcome back, everybody. Shh, settle down. Okay, since I'm going to ask everybody to close their laptops, since it's clear they'll be working on code if I don't. So close your laptops. No laptops. Keep them closed. Come on, you can do it. All right. So close your laptops. Okie doke. So last time we talked a bit about deadlock, and hopefully you talked about deadlock on Friday as well. But one of the first things we talked about was the difference between starvation and deadlock. So starvation is a general condition in which threads wait indefinitely, whereas deadlock is a very specific type of starvation which won't resolve itself because there's a cycle. Okay? So we gave 4 conditions, and these are preconditions for deadlock. If you can get rid of any one of these, then you won't have a deadlock. So they were mutual exclusion, which basically says when one thread has a resource, the other one can't. We have hold and wait, which is a situation in which a thread grabs a resource and then goes and waits for a different resource. So it's holding on to the first one while waiting for the second one. No preemption, which means basically it's not possible to remove a resource from somebody once they have it. And circular wait, which is thread 1 waits for 2, which waits for 3, which waits for 4, which waits back for 1. Okay? If you don't have one of these conditions, you're not going to be in a deadlock. Were there any questions on the conditions? We good on that? Okay. We also introduced this resource graph idea. And this is a very clear way of showing whether you're in deadlock or not. And remember, the little rectangles could have 1 or more dots in them. They represented resources. Multiple dots were resources that were essentially equivalent. This means, for instance, resource 4, you could have any one of these and you'll be happy. Then the circles are the actual threads, and the arrows are waits for threads, or waits for arrows, essentially, which the thing at the tail of the arrow is waiting for the thing at the head. So, for instance, arrows going from threads to resources are cases where the thread is sleeping, waiting for a resource. Arrows going from resources to threads are cases where a resource is owned by the thread. Okay? And as a result of these kind of graphical models, we can basically walk our way through and find deadlocks. So, for instance, this has got a deadlock, and if you look, you'll see it never resolves. So this is a case where some thread's waiting for a resource, which is waiting for a thread, which is waiting for a resource, which is waiting for a thread, which is waiting for a resource. And this resource will never be available until either T1 or T2 are free, and of course, they're part of the cycle. So we have this cycle here, which is an actual deadlock cycle. And of course, the cycle on the far right is an example of a cycle that isn't a deadlock cycle. So notice that just because you have a cycle doesn't mean you have deadlock. Okay, that's only one of the 4 conditions. Okay? Were there any questions on this? Now, how can you tell whether there's a deadlock or not here? What do you have to do? Yeah. Yeah. Remove the threads that can finish, and then what? So you skipped a step. Remove the threads that can finish. So these threads here aren't waiting on anybody, so they can finish. Put their resources back into the pot, and then see whether threads that were formerly waiting can now make progress. Let them finish, put their resources back, and so on. So it's like a mental simulation where you're working your way through. You start with the threads that can finish now. You put their resources back. Now can new threads finish? Okay, put their resources back. Okay? All right. Any questions on that? Now, I showed you at the very end of the hour, and we'll go back into it, a deadlock detection algorithm, which essentially just simulates exactly what I said there. Okay? And that was, I tossed that up at the very end, and we'll make sure that everybody's got that. So then the question, of course, is if you find a deadlock, how do you handle it, or how do you handle deadlocks in general? One is you actually let them happen in the first place, and then you recover somehow. Okay? So first of all, this particular methodology requires you to be able to detect the deadlocks to start with, and then it needs something to get out of the deadlocks. Because remember, deadlocks don't resolve themselves. Okay? We could make sure that the system never gets into deadlock. Now, it turns out what we'll show today, using the Banker's algorithm, which I hope you guys heard about on Friday, right? You started the Banker's algorithm. We'll definitely go over it again. But basically, the Banker's algorithm kind of bootstraps the deadlock detection algorithm and uses it to make sure that you never get in deadlock in the first place. The downside of the Banker's algorithm is you have to monitor all of the lock acquisitions and frees in order to selectively deny those that are going to cause a deadlock. And so this is potentially expensive, even though in principle it's doable. And we'll talk about the fact that there are even some holes in that. And then the last thing you could do is you could just ignore the problem and pretend there's never a deadlock and Control-Alt-Delete when it happens, right? Or throw your computer against the wall or something. Unfortunately, this last example is all too common. Okay, and the reason it's common is, one, people don't do the analysis, so they don't really know whether deadlocks could happen or not. And so, of course there are no deadlocks because I can't find it on this really quick 2-second look at my code. The other reason is there is some expense to actually either detecting or recovering from deadlocks, and so sometimes people decide that the probability is low enough that they can afford an occasional deadlock and make you reboot. Okay? So surprisingly, that is considered an okay systems design method, unless, of course, you're doing something like running a nuclear reactor or something, and then you don't want to do that. Okay? All right. So today, I want to talk about how to prevent deadlock, and then we are going to dive right into scheduling. Okay? So without further ado, let's pop up this algorithm we started with last time. And keep in mind that this algorithm, as messy as it looks, although you guys are Berkeley students so you can handle messy-looking algorithms, is really just the graph algorithm I sort of implied earlier, where you kind of mentally work your way through all the threads. That's all this is. And the nice thing, if you only have one type of each resource, which means those little rectangles only have one dot in them, all you really need to do is take that graph and look for cycles. A cycle will mean deadlock if you have only one of each resource. It's really more interesting if you have more than one of each resource, and so that's when we need a more general deadlock detection algorithm. And here's the graph here to just keep in mind. And remember what we said, we find the threads that can finish, that's T2 and 4, we put their resources back. And then, oh, gee, that means T1 can get this resource, then T1 can finish, and it can put that resource R1 and R2 back, and T3 can finish, and so on. And when we're done, we've finished all the threads, and nobody's waiting anymore. Okay, very straightforward. And so how do we formalize this? Well, basically a bunch of vectors where the number of elements in the vectors equal the number of distinct resources. Okay, so in this case, there's only R1 and R2, and so these vectors all have 2 elements in them. And the first vector is the free resource vector, and that's basically the number of each type of resource that's free. Now, in this particular graph, what does the free resources vector look like? How many people think it's 0, 0? Okay, you'd be correct. Why is it 0, 0? Well, because there are no R1s free and there are no R2s free. 0, 0. Okay? The request vector, there's a request vector for every thread, and it represents the resources currently being requested. So if you look here, for thread 1, what is its request vector? 1, 0, right? Because it's requesting 1 R1 but no R2s. Okay, and the request vector for T3 is 0, 1, right? And these guys are 0, 0. And then the alloc vector is the current resources held by the thread, and that's easy. What's T1's allocation vector? 0, 1. All right, you guys are on top of it. Now that you got that, we just toss a little list-based algorithm at this. And what we say here is that we take the total number of free resources, and we put that in an available vector, and then we're just going to work our way through until we can't go any further. So we put all the nodes, or these should be threads, all the threads into the unfinished category, And then we go through, and for every unfinished thread, we say, gee, are the number of resources I need less than or equal to the number that are available? And notice that this is a funny comparator operator, right? This basically compares pairwise for each, the first element here with the first element there, the second one with the second, third with the third, and so on. And basically, if every one of those is less than or equal to, it means that this particular thread could allocate resources enough to finish. In that case, we remove it from the unfinished threads, and we put its resources back in the available pot. We say, gee, we're not done yet. We've made some progress, and we keep looping. Okay, and then when we've gone through all the threads for the first time, if we're not done, we go back and do it again and take the remaining threads, and we just keep doing this until we run out. Okay, and run out means either we don't make any more progress or there are no threads left in the unfinished category. Yeah, question?
So doesn't this algorithm depend on our order and allocation? So, for example, we have T5 that require resources both R1 and R2, and then T2 finishes, and then T5 happens to get R1. In that case, it would be a state of deadlock, whereas if T1 got R1 first, then it would not be.
Okay, so that's a great question. So the question is, doesn't this depend on ordering? And the answer is certainly. What this is telling us is whether there is an ordering in principle that would finish. Okay, it doesn't say that a scheduler would be smart enough to find that. Okay, that's a good question. All this tells me is that is there an order for which this will finish? Now, to get a scheduler that would find that ordering is very tricky, because in general, the scheduler doesn't know the graph. And so that's where the banker's algorithm will be an example for which the scheduler will know enough about the graph to avoid deadlock. But that's a good question. Okay, any other questions? Does this make sense to everybody? This is just doing the simulation I said. Now what are other things that might be broken about this notion? This says, is there an ordering that avoids deadlock? Okay, suppose it says yes. We already know one instance where it may still deadlock, which is the scheduler picks some other order that picks a cycle. What are some other ways in which it might cause problems? Yeah?
This thing itself get deadlocked, like, there's still things in unfinished, but then the if statement is true.
Now, fortunately, this thing actually terminates because it starts with done true, and if you make it all the way through all the threads and don't find one that makes progress, then you exit. Yeah?
T4 or T2 could be joining on T1 or T3 in such case that
Okay, so there could be hidden synchronization that we don't know about in this graph, which is that T2 is, say, joining on T1 and we get a cycle. So the assumption has to be that all resources, including threads that you might join on, are explicitly represented in the graph. Otherwise, you got problems. That's good. What else? Yes?
we assume that when a thread is not waiting for anything, it will finish.
Yeah.
No matter what, like it won't, let's say, go to acquire a different lock.
So there's a pretty big assumption here that somehow, for some reason, that when a thread can finish, it will. There could be a bug. Right? The thread could go into, an infinite loop, and then we'd certainly never finish, okay? So, yeah, so this is an idealized deadlock detection algorithm, but it's assuming that, assuming the threads are behaving reasonably and it's got all the information in it, then there's a potential to get out of deadlock. Okay. So what do we do when we detect that deadlock? So, by the way, detecting deadlock is the example in which we make it all the way through this, and there's still some threads left in the unfinished category. Then we know we've got deadlock, because there was really no way to finish everybody. Okay? So what do we do when we detect it? Well, one case is maybe we just terminate the thread and force it to give up resources. Remember the bridge example from last time? This is the Godzilla reaches down, grabs a car, tosses it over the side. No problem. All right? I guess you could shoot one of the dining lawyers. The problem is, of course, that this solution's not always possible. If you were to kill a thread, you might actually leave your system in an unstable state. Okay, because who knows what it's got? It may have grabbed resources that are effectively locks but outside the system, and then you got a problem. The other thing you could do is preempt the resources without killing off the thread. Okay, and remember, if we get rid of preemption, we don't have a deadlock. The problem with that is basically the semantics of your computation may suffer. For instance, a resource might be a lock in a critical section. If we preempt that lock, suddenly there might be 2 threads in the critical section, and then we've got bad computation. Because the whole point of the resource there in the case of the lock was to make correct computation. Okay? Now, another thing you might be able to do if you're carefully designing your system like a database, for instance, is to roll back the action. So the thread's been doing a bunch of stuff, but you keep enough of a transaction state there that you can undo everything. So effectively, you pull the thread back to the point before it grabbed all the locks. And in that case, you can effectively preempt the thread and get out of the deadlock cycle. All right? And this is very common in databases, that what they do is they run a deadlock detection algorithm, and if there's ever deadlock, what they do is they actually roll back the threads. Okay? So this is a case where you can actually detect deadlock, roll back all the state, and effectively get out of deadlock. Okay, now, unfortunately, this is very specialized. It's for databases where the things the threads might be doing are very specific, undoable data change options, and that's not always possible. But it is nice to have this ability when you have it. Okay, and many operating systems use other options like, yeah, just reboot when you get a deadlock. Okay. Questions? So what are some good techniques for preventing deadlock? Well, one of them is infinite resources. Okay? Now, this is the example of the Bay Bridge, 12,000 lanes, no problem. Okay? You never end up waiting. Unfortunately, the freedom of infinite resources is not always there, but I will tell you there are some instances where you could approach that, like, for instance, the amount of memory being put in machines and server machines is a lot, or the amount of disk space in the world is huge. And so in some cases, you might be able to treat those as effectively infinite. And if you've got a situation where there's some buffer you're waiting on and you're in a deadlock loop, just by adding more space in the buffer, you can often get yourself out of deadlock. And so this effectively infinite solution is not as weird as it sounds. Okay? You could make sure that you never share resources. Never sharing resources basically gets you out of what things in the four, what are the 4 conditions do you get out of with never sharing resources? Which one? Mutual exclusion. Yeah, I guess you would never, you probably still have mutual exclusion because you'd want to make sure that, yeah, I guess you're right. Mutual exclusion is effectively not an issue because you can never share. Okay, I'll buy that. Yes. Okay, no synchronization, but specifically, how do we get out of deadlock, though? Yeah. Yeah, there's no hold and wait, right? I mean, there's never a situation where I'm waiting for a resource owned by somebody else because it's just not possible. Yeah. Okay. Now, if we don't allow waiting of any sort, we're never going to deadlock either. Okay, so this is actually how the phone company avoids deadlock. Believe it or not, what a busy signal often means is, that there was a path that tried to open up and it wasn't immediately available, so it bounced the busy signal back to you. Now, what we're effectively doing there is getting rid of hold and wait. Okay? We're also getting rid of cyclic wait because there's no way to get a cycle because you never wait for anything. Okay? So I guess both cyclic and hold and wait kind of go away. This is actually a technique used in some networks. Okay, so we'll talk about Ethernet later in the term, but how many people are familiar with the collision algorithms that they have in various networks like Ethernet? Any of you? Okay, so we'll talk about this later, but the idea is both people start talking at the same time, and they detect a collision, they both back off at some random time, and then they try again, and one of them makes it through. Okay, and basically what this is again doing is getting rid of hold and wait, and therefore we never get a deadlock. Okay, now there is some inefficiency there, and this is why Ethernet and some of these other algorithms can never get 100% throughput, because as you have more and more requesters in here, your efficiency gets to the point where you kind of level out because everybody's retrying. Okay, and so there is some efficiency. Consider the case where you drive to San Francisco. Every time you hit a traffic jam, you're suddenly teleported back home. Okay? That would be pretty annoying, but that's kind of what hold and wait is like. Okay? And you got to combine that with 12,000 lanes, and then maybe you'll actually make it to San Francisco. Any questions on these first ones before we talk about more practical ones? Okay, so another technique is we could make all threads request everything they need at the beginning. So if everybody always requests everything they need, then we either give them all their resources or not, and therefore they're never doing a hold and wait scenario. Right? You either get everything you need up front or you don't. Okay, we just got rid of deadlock. You know, if you need 2 chopsticks, you request both of them at the same time. Or you don't, you know, leave home till you know nobody's using any intersection between here and San Francisco. Okay? Now, of course, what's the downside of this? Yeah.
Could you have something like the server running, like essentially if you have something that's intended to run forever, you're going to have to either have all the resources ever, or you're going to have to turn off that process.
So if you've got a long-lived thing and it's going to request a lot of resources up front, then you've got to have enough resources to run it. That's certainly true.
So essentially you have to make sure that they have to be taken off the resources.
Yeah, so I think the thing to be careful about here, so I'll agree with you in principle, is that you have to ask yourself, how would something like that run anyway? And it probably would end up asking for resources and then internally doling them out or something if it's really a server. So, but yeah, okay, you'd have to. The problem with this is what you're saying here is essentially you have to request everything at the beginning, and if you've got multiple things that might need to share those resources effectively with because of mutual exclusion, you've sort of gotten them yourself and nobody else, especially if you're infinitely long. Okay, I'll agree with that. What else might be problematic about this? Yeah. Can't have a real-time system. Why is that?
You won't know until like calculate later in the process life cycle when certain resources.
Maybe. What if you just ask for more than you need?
How do you know how much you need?
Okay. I mean, essentially, what you're hitting on here is essentially maybe you don't know what you need up front. Sure. I mean, that's kind of one of the big problems with this is you don't know what you need up front, and it's not very good for long-running things that go forever. I will agree with that as well. Okay. So here's another option. You force all resources to be requested in an order. You take all resources in the system, you sort them, and you never request resources out of order. So you ask for an X and then a Y and then a Z and then a Q and then a W, whatever. Why does that eliminate deadlock? Yeah.
Resource acquisition by certain threats is preferred for certain threads over others.
So this is not actually preferring resources from one thread to another. This is making sure that when I acquire resources, they're always in an order. It's a little different. So there doesn't have to be priorities to make this work. Yes?
There's no cycles
Why are there no cycles?
because everyone has to access them linearly. So you can never, someone can never have a resource farther down without like having all the ones up that they need.
Okay, so the way you prove this deadlock free is you say, how do you do this? You say, assume a cycle, right? If there were a cycle, what would that imply? Well, the only way that there could be a cycle is if you actually have somebody who's got a later thing like Y and is waiting on something earlier like X. And I challenge you to take a look at that, but you'll see that all cycles would require that kind of a loop, and because we've explicitly disallowed that, there can be no cycles. Yes?
Can you just discretize it in time so you can pipeline everything and everything is ordered, therefore any process that also obeys the same order can be pipelined as well, and therefore you can guarantee that they'll never have a deadline?
Yeah, but I'm not sure you need to quite go to that level of complexity. I think you just basically assume a deadlock graph. Okay, this is a simple way to do it. Here's a graph. You don't have to figure out how to get in there or how did I get there. Well, just assume any graph that's deadlocked and then say what's implied by it. And gee, that implies that we would have somebody already with a Z waiting on an X, and therefore that can't happen. So that would, I think that would be a simpler way to go after the deadlock, is just assume any deadlock cycle, what are its properties? Question, yes?
Couldn't you fix this like at the compiler level by ensuring, like running a graph on the code and ensuring that it's not possible to get?
Yeah, the problem with having the compiler really ensure this is you have to make sure that for all execution paths, there isn't one that does something out of order. And that gets a little dicey. It gets a little close to the halting problem under some circumstances. So, okay. So remember, of course, that I showed you explicitly this resource allocation with wormhole routing last time, where I said, networks that kind of always go east-west before north-south don't have deadlocks, and that's exactly because we've actually eliminated this turn, and therefore if there were a cycle, it would have to have one of these turns and those turns, and therefore there's no deadlock. Okay? Now, what's interesting about this is how many total turns are there? Well, 1, 2, 3, 4 possible turns going clockwise and 4 going counterclockwise, so there's 8 possible turns in a graph like this. And we've disallowed how many? Four of them. You can count, right? Because 2 of them going one way and 2 of them going the other way. It turns out that you can actually disallow only turning west, for instance, from north or south, and therefore never get a deadlock as well. So you can get by only disallowing 2 out of the 8. So that's a slightly less constrained graph. But again, how did you prove that? Assume there's a deadlock. Well, look, one of them's got a turn west turn in them, therefore this can't happen. Okay, questions on this? You see by the way, does everybody see why I extended this graph to be repeated in all directions here? Can somebody explain that to me? If I'm really going to force x before y? Anybody? Bueller? Think about what this train was doing. This train was going like this and then this, right? That means that there's some source up here and some destination here, which to get from here to here, the train was doing that. But if I'm forcing x and then y, and I only had these original tracks, there's no way to get from here to here by only going like this, right? Just isn't possible. So by basically extending this graph in all the directions, what I make sure is that, yeah, there is a way to go the x part first in that way. So this train, rather than doing this, which is disallowed, would actually go like this, up over top and down. And so that's why we have to turn this into a mesh. So that rule here actually has some consequences in the topology. But you have to be a little bit careful. When you state a rule, you have to make sure that you can follow it. Okay? Good. So let's talk about the banker's algorithm. So the banker's algorithm is, in principle, very simple. The idea is, don't ever let a graph occur that might be deadlockable. Okay? Now, let's start our way along this. This is a little over-conservative, but basically, assume that everybody up front has to state the maximum resources they'll ever use. Now, notice this is different from getting all my resources up front. What it says instead is, here's the most I'll ever use. It's a little different. Everybody with me on that? I'll say, well, I'll never use more than 4 disks and 2, whatever, network cards or something. But it doesn't mean that I have to use all of those at once. Okay? And now, this is an idea here. Whenever I go to request, the banker says, well, you requested 2 disk drives. Let's take a look at how many I've got available. Let's say I've got 3. And you requested 2. So, gee, if I give you those 2, there's only going to be 1 left. And is that 1 greater than the max remaining that might be needed by any thread? Sort of like, okay, I'll think about whether I can give you those 2 disk drives, but let me make sure. Let's see, I'll only have 1 left. Is that enough to make sure there's no deadlock? Okay? And why can I do that? Well, I can do that because I know what the max required by everybody is. Okay? And somebody tell me why there will be no deadlock if I follow this, and then somebody else tell me why this is over-conservative. So let's start with the why is there no deadlock if I follow this rule? Yeah.
You always have enough resources for anyone else to request it.
Why do I always have enough resources?
Because you know what the max is. Therefore, if anyone else it never exceeds that max, then you can guarantee that everyone else can also get the same resources.
So basically what we're saying is, so if I have that one disk drive left, I look at everybody remaining, and if nobody's ever going to need more than one more disk drive, then clearly I'm not in deadlock because by my little simulation algorithm, I finish one of them, put their drives back, finish more, and so on. Okay, does everybody see that? Now the more important question is, why is this over-conservative? Yes?
All you need is the one that needs the least amount of disk drive, to finish, and then he'll at least get resources. So even if there's a thread that needs two, if there's one that only needs one, and that one can take the disk drive, do whatever it needs to do, and finish, then you prevent deadlock by moving.
That's exactly right. So for instance, taking my example, there were 3 left. I took 2 of them, and there's only 1 left. It doesn't necessarily have to be that nobody needs more than 1. All we need to make sure is that somebody can still finish and put enough back that everybody can finish. Okay, so think back to our little simulation thing, right? You put a graph up, you try the graph. We say, suppose that we give Kubi's thread 2 disk drives. Let's make the graph. Can we simulate it through and get a non-deadlock graph or not? If the answer is yes, then we win. If the answer is no, then we got a problem. Yes?
How do the threads know the maximum resources that we don't?
So how do the threads know the maximum resources that they need? Well, that's a good question. We have to assume that they can do that. Otherwise, we can't use the banker's algorithm. Okay, so somehow you've got to come up with that number, and that's part of playing ball here. Good question. Any other questions? Okay. Now, the banker's algorithm is exactly this. Allocate resources dynamically, just like we might have done otherwise. We evaluate each request and grant if some ordering of threads is still deadlock free afterwards. So basically, for each request, I'm going to create a little graph and say, is the resulting graph deadlock free? If the answer is yes, then I'll let you have your resources. If the answer is no, I won't let you have your resources. Okay? So we just take our deadlock detection algorithm we had earlier, and we're going to replace what we had before, which is if I look at the current requests from any node, and we say, is it less than what's available, with, well, I'll take the maximum I said that I might have minus the amount I have, okay, and that's now becomes my maximum request that a thread could have over and above what they've got, and if that's less than what's available, then I can simulate. Okay, so it's basically just walking through that graph. Okay? Now, of course, there's a name for what we're doing here. We're sort of keeping the system in a bunch of what are called safe states. And a safe state is one for which there is a sequence of threads, 1 followed by 2, followed by 3, followed by 4, such that everybody finishes. And as long as we always keep the system in a safe state, then we're good to go. Okay? Now notice that my notion of finishes in this instance is against the maximum. So basically what we're assuming is take the system as it is right now. I know it's a safe state if assuming that everybody were to ask for the maximum resources right now, that I could still simulate my way through. Okay? Okay. And it turns out that this is actually a little bit on the conservative side. Why? Well, because I may request resources. The assumption here is that I never give them back until I'm completely done. Okay, but it's perfectly possible that I could be grabbing resources, returning them, grabbing them, returning them, grabbing them, returning them. The banker's algorithm will still prevent deadlock, but it may be a little conservative about who it allows to have resources because it can't assume that a thread's going to be good and give up resources until it's done. Okay, so real threads might actually behave less conservatively than the banker's algorithm requires. And that's why we call these safe states. They're basically safe according to a certain assumption, which is that threads are never going to give up resources until they're completely finished. Yeah?
When obviously you run the banker's algorithm every time someone requests.
Yep.
You also run it every time someone gives a resource back.
Yep, you have to run the banker's algorithm on all requests and returns, yes. And you have to, every time a thread starts, it has to actually say, here's my maximum I'm ever going to request. That's another requirement here. Okay. Say again?
Why did it need to be run on return?
Well, because what's on returns, we have to update our available vector. Okay? So because the basic assumption is at least when a thread finishes, it gives all its resources back. So certainly that has to happen at the end of the thread. Say again? Well, you don't have to reperform checks when you're giving resources back because the banker isn't prevent somebody from giving resources back. They're only preventing somebody from getting resources. Now, the other question you might ask is what happens if the banker does its calculation and decides that you can't get 2 disk drives right now? What happens? That's right. You go to sleep kind of on the banker, I guess, or something like that. Yeah. Okay. Questions? Good. So here's a good example. So we have the dining lawyers. Remember this, you're safe if it's not the last chopstick or if it is the last chopstick, but somebody will have 2 afterwards. Okay, why is that following the banker's algorithm? Yeah, go ahead. Okay, so let's take this first example here. Suppose I'm asking for a chopstick, 1 chopstick at a time, and it's not the last chopstick. Okay, so why does that come out okay with the banker's algorithm? Right? I already have 1. There's 1 left, so I know at least I can finish. Grab 1 more, finish. I'll put 2 back, and now everybody can go on from that point on, so we're not deadlocked. Okay? Now this last example here is the last chopstick, but at least somebody will have 2 afterwards. Doesn't matter that I grabbed the last one. There's somebody else with 2. They'll finish, they'll put them back, and now everybody can finish. Okay? So see how that works? And that's a very simple kind of degenerate case of the banker's algorithm. This one I like here is the K-handed lawyer, right? And of course, that's in general. It's the last one, but nobody would have K. It's the second to last. Nobody would have K minus 1, and so on. If you work your way through the banker's algorithm, you'll see this also works. Okay? Good. Any questions? Yeah.
So you can only get a resource if the maximum that you'll ever need is at least as much as there are left in the system?
No. The way to think about the banker's algorithm is purely from a simulation standpoint. Suppose you ask me for something. I'm going to say, suppose I give that to you. I'm going to recalculate the graph. Take this graph, run it through the deadlock detection algorithm. Does this have a deadlock? No. Okay, here you can have it. Okay? The caveat there is the way I do that deadlock detection algorithm is I'm computing the ability of threads to finish against what they declared were their maximum ever requirements. So I'll assume that for a thread to finish, it has to eventually request all of the maximum resources. Okay? But it doesn't have to be on the fly that there has to be the maximum left for anybody at any given instance, just that this graph could finish. Okay? Good. Yeah.
Couldn't you just assume that the threads are going to use the resources that they have already been granted? Since you're running it every time a thread tries to grab a resource, you always know the state of what resources are in possession. rather than knowing the future, you could just assume that.
I think that's what we just said.
But why does each thread have to know how the maximum it will ever require?
So the reason a thread needs to know what the oh, I'm sorry, I misunderstood your question. Now I got it. So the reason that you need to declare what the maximum is that you'll ever need is in order to decide whether a graph is resolvable. You have to say, in order for a thread to finish, let's assume it requests the maximum it asks for. Because we don't know what the thread's going to do in the future, and we're allowing a more general scenario where things can be asked for over time.
But couldn't you assume that the threads are only going to need what they've been allocated so far? Because anytime they're going to be allocated an additional resource, we're going to run the algorithm again.
So the problem is, if you think about this banker's algorithm example here, if I ask for one resource, okay, I don't have any right now, but I know I'm going to need at least two. And you need the fact that I'm going to eventually need two to figure the actual deadlock. Yeah?
How can we do this with threads that require like a dynamic amount of resources that can't declare?
Can't do it with threads that require an unspecified maximum. That's a good question. So you're already seeing the limitations, right? Limitation 1, you have to declare your max up front. Limitation number 2, can't go into infinite loop, right? If you go into an infinite loop, all bets are off. Limitation number 3, you have to have a gateway to every request and return. Because if you can't see the whole graph, then you're basically not going to be able to run this algorithm. I mean, or it won't do the right thing, because there'll be information outside the algorithm and you could deadlock for other reasons. Yes?
How much does this slow down the system?
Potentially a lot. I mean, this could slow down the system quite a lot depending on how aggregate your requests for resources are and how low overhead you were counting on them being. So oftentimes people try to make lock acquisitions really low overhead. Question? You want to ask the same thing? Okay. All right. Good.
It would take like linear time, whenever you update threads.
Yeah, it's potentially linear in number of threads. Yeah, so this grows pretty rapidly if you're not careful. Now, what you can do, however, is you can arrange so that the graph is pre-constructed, and you kind of know what your exit case would be, and so you can kind of build a cached version of the graph. So you don't necessarily have to do all K simulations, but yeah. And I don't know what the actual bounds are on the best you can do here, but it's not as bad as what you say. That's a good thought. Okay. Administrivia. So officially Project 1 code's due tomorrow, but I have been hearing that there have been problems with the autograder. And I'm sorry that it wasn't fully functional until Friday, so we will let you turn your code in on Wednesday night, 11:59. But I don't want to get behind. So we're going to have you turn in your design docs as well on Wednesday still, okay? Because I don't want to get behind. So I'll give you the extra day on the code. You won't lose a slip day, but let's not get behind on things. And be prepared to dive right into Project 2, okay? Are people okay with that? Sorry about the auto grader. We'll make sure that it's better, that it comes up earlier next time. Okay? Don't use slip days. That would mean don't turn it in on Thursday. Okay, I would hope you don't do that. I mean, you're welcome to, but that would be a bad use of slip day. Okay, I'm giving you a free slip day, kind of. Okay. Group evaluation technically is the day after things turn in. We'll try to do them on Wednesday. Maybe I'll let you do it on Thursday. But you got to do this for every project, because if you don't do group evaluation, it's could lead to zeros on your project for you. We actually use these to help figure out how your team is doing. Okay, so and that's in combination with your TA's evaluation of how you're doing. So it is a zero-sum game. If it turns out that one of you is not contributing to your group, we will figure that out, and potentially your grade on the project will be lower than your partner's. So you got to make sure you're actually helping, okay? Now, we do occasionally get people that just have bad personalities, and they get, really bad evaluations because, I don't know, they just, their tweets are poorly worded or something. I don't know why. But we do account for that, okay? We do try to watch what's going on, but it is an important part of this. So you better make sure to do your group evaluation, and I will be nagging you about it. And if you don't do it, I will actually give you 0 on your project. So this is a requirement. Okay? Basic idea is you get 20 points for each of your partners, and you get to take the sum total and hand it out to your partners in any way you want, and they do the same about you. Okay? Now, hopefully, when you're doing that, you actually also put in some wording about how that works. But, why, what's your justification, and so on. But your TAs are also very aware of how your groups are doing. So, okay? I'll bug you about this a little later. I am going to bug you about midterm 1 because it's now 2 weeks away. Actually, it's 2 weeks from today. Yes, that's true. So should be a 2-hour exam with 3 hours to do it, although I've been known to give slightly longer than 2-hour exams. Closed book, 1 page of handwritten notes, both sides. Handwritten notes, both sides, 8.5 by 11, not, designer-style paper. You're not allowed to microfiche the book or anything and bring a magnifying glass. Those are not allowed either. If you have a conflict with this exam, you need to let me know sooner rather than later. And we do have a location, which is 155 Dwinell. There are things to study. Okay, there's plenty of midterm 1s up on the handouts page. So I would say use those. Oh, there's solutions as well. No class on the day of the midterm, so you actually can come to extra office hours that I might be holding in the office. And your TAs will have extra hours too as we get closer. Topics, everything up to the previous Wednesday. History, concurrency, multi-threading, synchronization, protection, address spaces will be topics that are there. Okay, history, that was lecture number 2. All right, any questions? Okay, everybody okay with the extension till Wednesday? Okay, anybody really pissed at the extension till Wednesday? Okay, I don't think you'd raise your hand maybe if you, sorry. You don't have to turn it in on Wednesday. The auto grader, I think, may still be running manually, but it should be running soon every hour or so. Okay. Any questions? No? Okay. So we're actually running a little slower today, so let's just take a break now. I'm sorry, I'm a little out of kilter here, and we'll start on a new topic when you get back. page is something that is one of the physical pages it's been given in. Okay. Now it may be that that ends up causing another page fault to pull in a different page from the virtual memory machine. Yes. Yes. In most cases, what they try to do with a virtual machine is make it think. The guest operating system think that it's running on a physical machine, so it gets all the page faults and everything as if it were on a physical machine.
Right, it's like available resources minus the number of resources.
Yeah, so that's a pairwise subtract. You're basically two vectors and you're trying to subtract. You're actually comparing them that way too.
I see. Okay. And which is what the graph algorithm is doing similar.
I've got class overlaps. Worst case, I can skip it, but it's just comment.
So, I realized that this question kind of came up in kind of a couple of different instances. So why the max? I think the way to look at this is we want to have a safe state be one in which when we look at our graph, we know for a fact that we can finish that graph. Okay, and that means we need to know everything that that thread might ask for in the future. Okay, because we have to take that into consideration. And if you look specifically here, this idea that I ask for one chopstick, as long as it's not the last chopstick, I'm okay, or is the last chopstick, well, somebody will have two afterwards. You can kind of see that the number 2, which is the maxes for these threads, are actually working their way into this decision here. Okay, so the number 2 is basically the fact that somebody has 2 chopsticks, that's their max, therefore they're finishable. So that's kind of why we need the max in this algorithm. All right, is that clear to everybody? So that's why the max actually comes into play, because we need to know that when they have 2, they're never going to ask for any more, and therefore they're finishable. Okay? All right. So now let's switch gears. We're going to talk about scheduling now. And if you remember at the third lecture or fourth lecture, I kind of showed you this path of processes or threads working through the system. We'll keep it with threads for now. And basically, there's the ready queue, which you all know and love now because of Project 1, is an obvious place to put threads that are ready to run but aren't quite running. And then we have a bunch of other queues which represent threads waiting on something. Okay? And we kind of talked about the life cycle of a thread, and active threads are basically kind of working their way, ready queue, CPU, ready queue, CPU, sometimes I/O. Here's an interrupt, actually time slice expired, so the case where you're just plain running flat out, you're actually coming out of the ready queue, running for a little while, going time slice expires, you get put back on the ready queue, and so on. That's just kind of part of multi-threading. And the question is, how does the OS decide kind of which one to pull off here? Now, fortunately, you're all well aware of FIFO and priority, right? Because you love priority schedulers, right? But those are instances of how do you make the decision of what to pull off the ready queue. And we're going to talk a lot more about when you make decision, how do you decide what to pull off the ready queue. Okay? And scheduling is basically this idea of deciding which threads that are given access to resources from moment to moment. Notice, by the way, that you could have a wait queue for a disk. The disk becomes free. Let's say you could schedule as to which one gets to use the disk. Okay, that's another scheduling algorithm. Now, the next lecture and a half or whatever, we're mostly going to be talking about how to pull things off the ready queue. But the ideas of scheduling certainly can be applied to any other queue on which things are waiting. Okay? So what are some assumptions? Well, scheduling was a big area in the 70s. Probably would have taken up a big chunk of this class, but fortunately for you, it's going to be a class and a half. But the thing that's interesting is there's many implicit assumptions when you start talking about scheduling. So for instance, one of the set of assumptions that often comes up is there's only one program per user, there's only one thread per program, and programs are completely independent of each other. Okay, do those still apply? Hard to say, right? In fact, I'd say the one program per user is certainly not the case. Okay, and one thread per program is definitely not the case either. So, and programs aren't independent. So maybe these assumptions are wrong. Now, clearly they're unrealistic, but they do give us a starting point. For instance, they let us talk about, so if we make those simple assumptions, we'll get more complicated in a bit, but we could ask ourselves about, well, suppose we want to schedule fairly. So what's the word fair mean? Okay, if I run one compilation job and you run 5, is it fair that I get 1/5 of the CPU you do? Is that fair? Or should it be the case that each of your 5 compilation jobs gets 1/5 of the CPU of my compilation job? Which one is more fair? How many people think the first one is fair? The more jobs you run, the more CPU you get. Okay, a couple of people. How many think it's more fair to sort of take each user and give them a fixed amount of CPU no matter what they run? Okay, some hands there. So notice we could actually probably have a debate here as to which is fair. And the answer is probably not clear that either of those are the only policy that should be run on a system. It depends on circumstances. It depends on what you're trying to do. But the high-level goal is to basically dole out CPU to users or threads or whatever it is according to some policy. And the first step is defining the policy. If the policy is to give you fair scheduling, you got to figure out what fair is. Okay? Now, one thing that we can do is we can say, well, what's the behavior of typical programs running? Well, what's kind of interesting is if you were to take all the programs running on a system, and then you were to sort of say, how long do they go for CPU before they hit an I/O operation? And you'd put a histogram, you'd actually see something like this, where there's a peak and then a long tail. Okay, can somebody explain why, if I'm graphing the amount of time that a thread actually uses the CPU, I get this kind of peaked behavior? Why is that? Yes? Okay, so it's hard to do anything without data. Okay, why does that cause this to happen? Okay, but why is it peaked like this? What is this peak saying? This peak is saying there's a lot of short bursts and some long bursts. Yes?
You're filling up your registers real fast, and then you have to save values out. You get
Okay, so you're thinking granularity registers. That's a little too fine-grained maybe for this. I'm thinking more I/O operations. You're on the right track. I mean, why are we have shorts and longs? Yes? So you're saying that this is because the I/O operations take a long time or because they're infrequent? So now if an I/O operation were infrequent and the thing I mostly do is compute, that would mean I'm mostly out here, right, in my burst size. This is actually saying kind of the opposite. This is actually saying that I/O operations here are frequent mostly, and then there's some long ones. Yeah, anybody else explain this? You see why it's a little different? Yeah.
It would seem that I/O is more of a continuous stream than any large batches that come in. So if you have a large batch, then you'd be able to do a lot of computation before having to switch back to I/O.
Okay. Well, what's the first thing you should ask? So, you know, Professor Kubi puts this graph up. I mean, you have to ask yourself, first of all, what are the assumptions? Okay, so the assumptions are something, I'm running a mix of something, right? Maybe, what if I tell you I'm running a mix of interactive and computational things? Does that help? Yes. Yeah. And what about, so we have to wait for user input, and then what happens when the user gives me input? What kind of input? Give me an input. Press a key, then what happens? While I press the key, I run a short little thing that maybe puts it up on the screen, then I sleep again, right? So interactive applications have a tendency to have a lot of short bursts while they're waiting for the user, and then maybe there's periods where they compute something, like they put up a picture on the screen of some sort. Maybe they render some cool scene. Those rendering operations might be the things that have the long tail, but the interaction with the user is the short tail. And so if we're mixing things together, we've got a bunch of these a bunch of these situations where we run for a very short period and then wait on the user, and then others where we run for a long time. Okay, so that's what this graph is saying. Okay, and clearly this is application and application specific. It depends on what the mix of apps are. If you had some machine whose sole job it was to play chess, it's possible that it would, spend most of its time computing. So the mix would be different. Okay, so clearly we're talking about some sort of mix with user interaction, and so our model here is that programs are alternating between bursts of CPU and I/O, and particularly we've got basically this particular graph is assuming that there's a bunch of interaction and then some long computing, but in general, we've got things run for a burst and then they do some I/O and then another burst and do some I/O, and what we'd like to do is we'd like to craft our scheduling around knowledge about how this application is going to run and use that to meet some goals of the system. Okay, so what goal might I see here? Or what goal might I want based on this graph? Yeah. Okay, I want to make sure that they get the CPU during their burst. Now, almost by definition, the burst is when they have the CPU. So, but how would I, if I had a whole bunch of things on the ready queue, how might I want to schedule them? Yeah. Okay, and so prioritize them based on frequency I/O in what sense? Okay, so you'd like processes that do I/O frequently or therefore have short bursts get a high priority. Why? Avoid annoying the user. Okay? Yeah. There you go. So basically, based on things looking like this and the fact that these bursts tend to be ones which would annoy the user if they were descheduled for long periods of time, might lead us to say prioritize the short bursts and give lower priority to the long bursts. Good. I'll buy that. Okay? And of course, these long ones, since we're time slicing, these actually might represent situations where you run for a while, but then you're forced to give up the CPU. Okay. So the assumption we're going to be making here is that there are bursts, and we're going to make scheduling decisions based on the burst. Okay? So what are some goals that we might go after? So one, we might want to minimize response time, which was just brought up. And here, we might want to you assume that you've got somebody sitting in front of the computer, and you want to minimize the time they wait. Okay? Because response time is what the user sees, the time to echo a keystroke. Okay? Now, I actually remember when I was freshman or sophomore trying to write a paper on a time-sharing machine, and it was so bad that you'd type a sentence before you got to see any keystrokes. It'd be like, to be or not to be, that was the question. Anybody experienced that before? I've actually heard that you guys have systems that do that, which is just bizarre. What are these instructional systems or something? Or is this kind of like network, maybe playing with tweeting or something? No, I guess that would be fast. Yeah, so that's annoying, right? What you'd like is you press the letter T and it should show a T, right? I mean, it's very disconcerting when you're trying to be creative. I mean, I do my best work. That to be or not to be was one of my better speeches. But it's kind of, I'm kidding. It's kind of hard to be creative when you're not getting fast response time, right? And real-time tasks have to meet the deadlines. I mean, imagine a pacemaker that has that problem, okay? All right, by the time you figure it out, you're dead, right? Okay. There was a question here somewhere. A comment? No? So minimizing response time or average response time might be very important. How about maximizing throughput? This is a different scenario where what we want to do is we want to make sure we use every cycle we've got because we're computing something like chess or something. And we're really more interested, rather than throughput, we want to maximize the number of operations per second. And notice that there's a couple of things. We have to minimize overheads, and that means basically not switching a lot, because remember, switch is an overhead. Want to make sure that we don't overuse the CPU or the disk. We're not swapping all the time. These are all about throughput, not about response time. And in fact, what you find is maximizing throughput and minimizing response time are often kind of going against each other. Can anybody tell me why that might be true? Yeah.
Pipelining, for example, allows you to have more bandwidth, but as you increase your pipeline, you also increase the likelihood from one stage to the next stage.
Okay. Okay, I'll buy that. So pipelining, deep pipeline, higher throughput, higher latency. Okay. What about the specific instance of somebody with keystrokes? Yeah.
Well, maximize throughput, you want to minimize context switching, but in the case we were talking about where you want to prioritize things to do a lot of I/O, you want to do a lot of context switching. You want to give something CPU, do the thing, and then switch out.
Yeah. So in the specific instance of interacting with the user, we want to make sure that those little bursts get the CPU more often than the long bursts. But the long bursts are the ones that would get the best throughput, right? So we're actually working against each other here. And fairness is not about minimizing average response time usually. Usually you get better average response time by making the system less fair. So if somebody happens to be typing a lot, they get more CPU than if they're computing. Okay, I don't know, is that fair? Hard to say, okay? Maybe it is. So the first scheduler, of course, we'll talk about is the so-called first come, first serve, or FIFO scheduler. This was, if you remember your history, right, this was the batch scheduler of old. This is the auto grader of new, right? And the idea here is, it's a line, right? And the idea is the first one in line gets to run, then the next one, then the next one, then the next one. Back in the original computer days, it meant run the whole thing to completion. That's incredibly wasteful now. So now it means basically run your burst until you do I/O without ever interrupting. Okay, and then once you, try to do I/O, you have to go to the back of the line. Okay. So here's an example. Suppose we have these three processes, 1, 2, and 3. Process 1 has a burst time of 24. Process 2 has a burst time of 3. Process 3 has a burst time of 3. Here is a Gantt chart. Everybody familiar with Gantt charts? This is where you sort of lay out your timing. Okay, often these are for scheduling people, but it's a good thing to figure out for scheduling processes as well. And notice that if process 1 runs to completion, then process 2 and process 3, we get kind of this situation where there's 24 time units with nothing but number 1, and then another 3 with number 2, and another 3 with number 3, and we're all done 30 time units afterwards. Okay? And we can kind of say, suppose your person, see, I'm mixing my metaphors here, person 1, person 2, person 3. Notice that person 1 has to wait how long before they get started? 0. So they're happy. Person 2 has to wait 24 units. They're not so happy. Person 3 has to wait 27 units. And this is before they actually start seeing output. Okay, is everybody with me? So what's the average completion time? Well, the average waiting time here for everybody, average waiting time is that P1 waits 0, P2 waits 24, P3 waits 27. The average over 3 is about 17. So what we've got here is average waiting time of 17. Okay? Question? Yes?
How are you supposed to know beforehand how long the process is going to burst for?
Magic. Question is, how are you supposed to know how long it bursts for? I haven't told you how to do that yet. Crystal ball. Okay, so assume that we know for a moment. We'll have to revisit that. Okay, good question. So now, we can also talk about completion time, and you can see that the average completion time is just when the jobs are over is about 27 units. Okay? Is everybody with me? So we could, as a metric of how annoyed the users are, we could talk about average waiting time and average completion time. Seem like a reasonable metric? Okay. Now, one of the bad things about first come, first serve is the so-called convoy effect, which is short processes get stuck behind long processes if they're unlucky. Right? Okay. So suppose that they're lucky. Okay, so P2 and P3 go first, and then P1. Looks, well, we finished 30 units in this there, so that's similar. But the distribution is very different. And now you can actually see that the average waiting time is 3 and the average completion time is 13. So people are happier. Okay? The average waiting time is much better. Before it was, here it's 3, before it was 17. Average completion time is 13 versus 27. So we seem to have improved quite a bit in our metrics just by reordering the processes. Okay, now, several things you could say to this is, one, how the heck would you know what the ordering is? Right? The second thing you could say is, does this really represent annoyance on the part of the users? And I actually think this is a pretty good metric of annoyance, right? Because it's, when do I start seeing some output from my program? Okay? So the pros and cons of the FIFO is it's very simple scheduling technique, but the short jobs get stuck behind the long ones, right? So, you know, you go to Safeway for some milk, and you're always stuck in the one, you know, the 5-item line behind somebody who manages to grab a cart full of stuff and justify that it's really, they got to be in that line, right? You never manage to buy. That's why I refuse to go into Safeway under almost all circumstances, because I can't just get milk. Okay, the best thing to do at Safeway is if you're going to buy 12 shopping carts worth of stuff, then it's good, right? Because you can't lose then. The nice thing, though, of course, is you get to read about space aliens, I guess, which is maybe fun. But so an alternative possibility here is the round-robin scheduler. And well, so first come, first served schemes potentially bad for short jobs, as you just saw here, right? So a short job is getting milk and being stuck behind the long something, right? And so that's, we basically got stuck here. Here we are, we're number 2 or 3, and we got stuck behind the large job. Yes?
If we assume that this is modeled people, then we assume that the happiness of each person are all equally weighted.
Right.
And then this applies. But if they're in sim processes and they're not attached to the two users, then we can't assume that the happiness of each process is equally weighted. It might be more important that the long burst run first, so that happiness is more.
So
It's tied to a certain model.
So you bring up a valid point, which is, how do we suppose that these are not really tied directly to people but are processes instead? What I'll still point out is that slowing down the long process by a little bit as a fraction of its overall execution time is a very small fraction, whereas for the short ones, they've gotten a rather major disservice by being delayed. So even from fractional increase metrics, it's still kind of be better to schedule them in this other way. So the round robin scheme is going to try to get around the sorry, when I made these slides, I was having fun with clip art. But so what we're going to try to do to fix this problem is we're going to try to shuffle the jobs around. Okay, by shuffling the jobs around, we make sure that the short ones eventually get some good place in line. Now imagine the supermarket example. You go to get milk, you're behind somebody with a cart full of stuff, and what happens is they get to run two things through, and then you get to go in front and run yours, and then they get to run the rest of their cart. Now that's completely impractical, probably likely to get your car keyed, but it actually is a good sort of analogy of what we like to do. And in a typical machine, we often deal with time quanta in the 10 to 100 millisecond range, where we're actually going to take the jobs in the system and we're just going to keep rotating them through. And as a result, the ones that are short will get to finish. Okay, and then the ones that are longer will keep going. All right, now you're hopefully all familiar with this, right? Everybody kind of thinks round robin is sort of an intuitive thing, right? Now, so we basically have a clock, goes off every 10 or 100 milliseconds, and when it expires, we go on to the next thing. And you can think about this a little bit simply here. If we have n processes in the ready queue and the time quantum is q, then each process gets 1 over nth of the CPU time max in chunks of most q units, and nobody gets more annoyed by waiting for more than n minus 1 times q units, okay? Because that's the worst that happens. Now, you can tune q to be as small as possible, and that will make you less and less annoyed, right? If I switch a lot, then I'm going to be less annoyed. What's the downside of switching a lot? Yeah. No, go ahead.
Overhead.
Yeah, overhead, right? Switching costs overhead. So if q is large, we get first come, first serve, right? If q goes to infinity, basically we run everything to completion. If q is really small, we get an interleaving. If it's really small, I don't know, if it goes every instruction or something, we get close to hyper-threading. Remember I talked about that early on, hardware micro-threading. So q, however, if we don't have hardware threading, q's got to be large with respect to the context switch time, or we're going to spend all of our time with nothing but overhead. Okay. Now, let's take a look at some examples here. So here we have some processes with some burst time. Process 1, 53, 2 is 8, 68, 24. Poor 8. Okay, process 2 is really kind of regretting being in this convoy. Okay, and if we take a look here, if we've got a quantum of 20, notice what happens is P1 runs for 20, then P2 runs for its 8. Oh, that's good, and now it's done, whereas before, if with first come, first serve, it would have had to wait 53 before it gets to run, and then so on. Okay, and all I'm doing here is, if the remaining quanta is less than 20, I run it out. Otherwise, I run 20 more milliseconds, or whatever this 20 represents, of the job, and I just keep switching. Okay? And if we look at the total waiting time, for P1 it's 72, P2 is 20, P3 is 85, P4 is 88. Average waiting times, okay, you can come up with those. Okay? And this average waiting time is going to be better than the average waiting time of a bad FIFO. Okay? Pros of this, it's better for short jobs. So you could say it's, I don't know, is it fair? Maybe. Context switching time adds up on long jobs. So a long job being switched out a lot ends up being longer than it would have been otherwise. Both because other things are in the middle of it and because there is overhead. Okay. So how do you choose a time slice? If it's too big, your response time suffers, right? If it's infinite, you go back to FIFO. What if the time slice is too small? Then your throughput suffers. That's because of overhead. So actual choices of time slice. So initially, the Unix time slice was a second. So think about that, right? If you got 3 compilations going on, now each keystroke is a second, right? Click, click, right? In practice, you need to balance sort of short job performance and long throughput. Typical time slice is 10 to 100 milliseconds. Context switch overhead is somewhere between 0.1 millisecond and a millisecond. So basically, you end up with about a % worth of overhead. So it's not too bad. Okay. Now, actually, here's a pretty good comparison just to close this out. So assuming 0 cost context switch time, so give me that for a moment. Is round robin always better than first come, first serve? Well, exactly. What am I talking about? Suppose we have 10 jobs, each take 100 seconds of CPU time. Round robin scheduler every 1 second, let's say. All jobs start at the same time. Notice the FIFO case, first job is done in 100, then 200 to dump 1,000. Round robin case, first job's done in 991, then 992, 993 to dump 1,000. Okay, so which one is better? Depends on what your metric is, exactly. So both of them finish at the same time. Why is that? Because I have 0 context switch overhead. Average response time is much worse under round robin, right? Because the average response time here is not too bad. Here, it's awful. It's basically like 995 or something, right? Okay, here it's more like 500. So, and cache state has to be shared between all of these threads. And so if you're talking at a hardware level, the round robin is much less efficient because I'm switching out the cache all the time. OK. So this is kind of fun. Here's a set of things that we're going to look at. OK, process 2, 4, 1, 3 has this ordering. We've been talking about that. This is the best first come, first serve example. And notice the best first come, first serve has an average wait time of 31. The worst has an average wait time of 83.5. The best completion time is 69.5. The worst is 121.75. You can see if the quantum is 8, I end up with about somewhere in the middle there. Okay? And we can fill this in. And notice how the shortest process, number 2, is basically stuck here. It's got the best first come, first serve is 0 wait time. The worst is 145. So the short guy has basically the largest variance. Okay? And notice how the round robin scheduler does a pretty good job of at least bounding how long I take. Okay? Whereas the long job, which is P3, it doesn't really care. You know, it's all kind of 85 across the board except for maybe the case of the worst first come, first serve. But basically, the point is the short jobs really benefit from round robin. The long jobs don't. But they don't really care that much. OK? All right. Good. So in conclusion, we'll deal with this. Let's see. Did I have a deadlock summary? We talked about the 4 conditions: mutual exclusion, hold and wait, no preemption, circular wait. We talked about deadlock detection algorithm and deadlock prevention. On scheduling, this is basically selecting a waiting process from the ready queue and allocating the CPU to it. First come, first serve scheduling is very nice because it's simple, but short jobs get stuck behind long ones. Round robin, giving each thread a small amount of CPU. It's good for short jobs, but it's bad when you have long jobs because they end up wasting a little time. And next time, we'll start talking about optimizations on top of both of these, like shortest job first and shortest remaining time first. All right, good luck. I'll give you till Wednesday night. See you on Wednesday.